Hi, I'm Austin Westbrook, and this is Lab 4. The purpose of Lab 4 is to analyze the difference in motion between an observed oscillating spring and a computational model of an oscillating spring. The main ideas we'll use is the energy principle, Newton's second law, especially the position and velocity update formulas, spring force, and spring energy. And here are our equations we'll be using. This is the velocity update formula, position update formula, force of a spring, energy of a spring, kinetic energy, and potential energy. And the result preview is although the position data of the computational model was similar to the observed model, we observed that the observed model lost energy while the computational model did not. This is likely due to air resistance. This is our observed experiment. The system is the spring and the weight. The surroundings is the earth. The initial conditions is that the weight is stretched on a spring and released from rest. And our only intended forces are spring force and gravity from the earth. We calibrated this data by finding the relaxed length of the spring and the initial length of the spring with the weight on it. And we found the K value to be 6.83 newtons per meter. This is the mass of the weight and the initial position. And on the side, we can see the data for the X position and the Y position. And here is our system in the middle. Our computational model, the essential code we used is we had to calculate L and our uh, spring energy and spring force to get S, as we can see here, the magnitude of the distance of the ball and minus the initial length of the spring. And here is our kinetic energy equation we saw in the introduction, and the potential energy equation, spring energy, and then the total energy is just all these energies added up. We know the force of gravity and the force of the spring, and those are the only two forces that should be acting on the weight. So our F net is just the force of gravity plus the force of the spring. And we use that F net to find our ball velocity and ball position with our velocity update and position update formulas. And then we just update our new spring position. And then down here, we're updating our energies and finding the difference between initial and new energy. And here's our data up here. As you can see, the change in energy is staying constant at 0 because no energy should be leaving our system. And then down here is it compared with our observed model. As you can see, the model is very consistent. The oscillating periods and distance it goes up and down stays the same, while our observed, there is a little discrepancy, especially in this Y. You can see we are losing some energy right here, which is likely due to air resistance. Possible error, as seen on the graph, the observed data does not oscillate consistently and even loses energy at some points. This is likely due to not accounting for air resistance or drag, and as some energy would be lost to air resistance. Also, by tracking the data in Tracker, I could have been slightly inaccurate. What does it mean? Um, According to the energy principle, energy cannot be created nor destroyed. Since we observed the change in energy in the graph to be 0, this agrees with the energy principle because the total energy in the system is staying constant, as you can see here on the right. For the next, what does it mean? Um, Here are our estimates for the oscillation times for our observed. We took the average of these green lines right here. According to the estimates, the oscillation period of the X component is slightly larger than the Y component. This makes sense as the weight has to travel a further distance to complete a full oscillation than the Y component. Seen on the right, you can see 0.1 to negative 0.1 versus about negative 0.6 to negative 0.76. So it's about double. Um, However, it's also only being affected by the spring force, so its oscillation period isn't significantly larger because there's no other force acting on it, such as gravity, to counteract the spring. And thank you.